This is lecture 19 for Chem 223. Today we're going to talk about peak shapes in chromatography and what affects those peak shapes. We're going to start off talking a little bit more about gas chromatography. So you remember we went over this schematic in the previous lecture, but one thing we didn't cover is that the column for the GC instrument is housed inside of an oven, and you can actually use that oven to enhance your chromatography separation. So let me show you what I'm talking about with some example data. So this is a sample of carbon species. So these are just carbon and hydrogen species. And what was done here is the sample was injected and all of these species were allowed to elute through the column at the exact same temperature of 150 degrees Celsius. And so what you'll notice is here on the left, we have a bunch of smushed peaks. You can't really tell them apart very well. And then way over here, you have super long retention times and somewhat broad peaks here. And so how can we improve all of this? Well, again, this was all run at a single temperature, right? But we can do something else where we can actually start at a low temperature and ramp up to a higher temperature. And this is a lot like a gradient elution in HPLC. But what that'll give us is much better separation of all the species and way shorter retention times. So why does it do both of those things for us? Well, in GC, things have to be volatilized, meaning they have to be in the gas phase. So if we start at a low temperature and slowly move up, the boiling point of all these species increases as the number of carbon atoms in the molecule increases, right? So as the size of the molecule increases. So if we start at a low temperature, we're just going to boil off the smaller species. And as we increase that, we'll increase the number of species we're boiling off. And since we're going to go to a much higher temperature, all of these other species, the other C species, are now actually going to get enough heat to travel through the column quickly. So what we've done then is effectively selected for which species we want to come off of the column at a given time. So we've made the retention times much shorter, and we've actually enabled ourselves to see a few more peaks in here that weren't there before. Now, of course, with everything, there's some pros and cons to doing a temperature programmed gradient. The pros are you get shorter retention times and generally much sharper peaks. The cons are you often get reduced detector sensitivity. So if you look at the intensities from when we were using the temperature gradient to when we didn't have the temperature gradient, we had much more intense peaks. This is especially true if you're using a thermal conductivity detector. Those are affected by the temperature of the mobile phase. And so if you crank up the temperature, the sensitivity just goes down. All right, let's go ahead now and talk a little bit more about how to analyze GC data. What I have here is just a chromatogram with my injection time at time 0, the air peak, and a peak for octane and nonane. And of course, we measure the retention times from the injection time to the top of the peak for each of these species. And then we also often want to measure the width of these peaks. Why do we want to do that? Well, the width affects how well these guys are separated. So you can see these two guys not perfectly separated. We don't have what's called baseline resolution here. And so we can try and measure the width of this peak at the bottom, but it gets pretty tricky because we don't actually know where this peak ends. You also run into issues with the background noise, which is going to make it hard to see when these peaks actually hit the baseline. So what we'll often do is we will go halfway up our peak and measure the width up there. And this is what we call the full width at half height, or the full width half max, or simply the width at half height. There's a lot of different words to describe this width, and they all just mean the same thing. And because these peaks are largely Gaussian in shape, since we can model them with a Gaussian, we actually know the relationship between the width halfway up the peak and the width at the bottom. And so we can actually get just as much useful information from measuring the width halfway up as we would from measuring it at the bottom. And we actually get more because we avoid all of the noise issues, or at least a lot of them, assuming we have good separation between these peaks. So what we're going to talk about now is how we quantify how well these two peaks are separated. So the way we quantify that is by using a value called resolution. So resolution is just a measure of how well we can tell two peaks apart. And it's calculated mathematically like this. So 0.589 times the difference in retention times of our two peaks divided by the average width of the two peaks at half height. So to give you an example of what we're talking about, if we have these two peaks here, the red peak and the blue, they have some retention time here and some retention time here. So then this delta TR here, this difference in retention time, is just the distance between these two peaks. So the one shows up at about 3.5 minutes, and the other one shows up at about 4.5 minutes. So there's a difference of about 1 minute in there. And then we take the width halfway up these peaks and take both widths and average them out to get this value. Now you'll notice that on this x-axis, we're using minutes as our unit. And so you can use minutes or seconds or hours, whatever, because the minutes will be in the top and bottom of this equation. So whatever unit you use for time will cancel each other out. But this is what it looks like when you have a resolution of 0.5. You can't tell that there's two peaks at all because they'll add together to give you this dotted line. So the dotted line is what you'll actually see on your detector. But if we have a slightly better resolution, let's say we have a resolution of 1, now you can clearly see that there are two peaks there. So you need a resolution of about 1 or really about 0.8 or 0.9 to tell that there are two peaks present. With a slightly better resolution, we get nearly baseline resolution here. Baseline resolution means that you can see the baseline in between the two peaks. So usually a resolution of about 1.5 is sufficient if you want to quantify these peaks. There's still a very small amount of crossover here, but it's usually not enough to prevent you from quantizing your analytes. I think your book might say that you need a resolution of 2 to do that, but the amount of resolution you need for quantitation is not that firm of a rule. Usually what you do is just report the resolution that you have for two peaks or a peak that you're trying to analyze, and then let people decide for themselves how much to trust your data. Then if you get to a resolution of 2.0, this is where you actually start getting your baseline resolution, where you get the baseline in between your two peaks. So let's give you a little bit of practice with resolution. Let's say we have an analyte that elutes with a 407-second retention time, which means it takes 407 seconds for the analyte to come off our column, and a half-height peak width of 13 seconds. A neighboring peak is eluted at 424 seconds with a half-height peak width of 16 seconds. What is the resolution between these two analytes? Go ahead and pause the video and work this out now. It's simply a math problem. Okay, this is how you should be doing it. So for your resolution, you just plug in the 0.589, then times the difference in retention times here. So it'd be 424 seconds minus 407 seconds. Then we're going to divide that by the average width at half height. So that's 16 seconds plus 13 seconds divided by 2. Notice that in this math, you'll have seconds on the top, you'll have seconds on the bottom. Those units will cancel out. And so resolution is a unitless value. So you should have gotten a resolution of about 0.69 when we take sig figs into consideration. Right. Is this baseline resolved? No, it's not baseline resolved. With this resolution, you might barely be able to tell there's two peaks present if you've been looking at chromatograms enough. Right. Next question, do all of the species have the same resolution? Think about this for a minute. Go ahead and pause the video and think about it, see what you think. Right, the answer is no. All species in a chromatogram do not have the same resolution, because resolution isn't a property of a single peak. Resolution is a comparison between two peaks. So you're calculating the resolution between adjacent peaks here. Right, now let's get into peak broadening and peak shape. So fundamental feature of chromatography is that your peaks spread out. And this just happens, so after you inject your sample and your sample travels through your column, your analyte is just going to get spread out into space. And the result of that spreading out, this band broadening, is that you reduce your resolution the more broadening you get. So we want to find a way to reduce that broadening. So to be able to figure out how to reduce that broadening, though, we're going to have to know where the broadening is coming from. So let's talk about 3 mechanisms for peak broadening. And these are basically the only reasons for peak broadening, and we'll get into some chromatography errors later, but they're slightly different than peak broadening. But the first mechanism for peak broadening is that as your analytes travel through your column here, I have 3 analyte molecules and a bunch of beads in my column, but as they travel through, they might take different pathways to get through that column and exit the column at different times. So here I only showed 3 molecules, but you can imagine if I had Avogadro's number of molecules traveling through here, then they're going to sample all of the different pathways that they can, and the different pathways are going to have different probabilities of occurring depending on how likely a molecule is to get there. And so what you get is a Gaussian peak coming out at the other end, where you have different arrival times or retention times for different molecules of the same species, but they're all relatively close together. So this first broadening mechanism is due to different pathways. This is also affected by temperature. And the next type of broadening is called longitudinal diffusion. So longitudinal diffusion, all this means is that your analyte is going to want to diffuse. So some of it's going to want to go left, some of it's going to want to go right. We don't care about diffusion up and down because analytes at the top of the column are going to exit the column at the same time as analytes on the bottom of the column. So we just care about longitudinal diffusion, not latitudinal diffusion. So as your solvents pass through here, they're just going to naturally spread out because that's what molecules do in the liquid phase. So the amount of longitudinal diffusion you're going to get is actually proportional to 1 over the flow rate. So here I have the flow rate symbolized by the letter U. It's also often symbolized by a mu. But if you increase the flow rate here, your analytes are going to A, have less time to diffuse before exiting the column because you'll be pushing them through quicker. They will also be under higher pressure because you'll have more solvent flowing through here at a given time, which just increases your pressure in the column. And so your analyte is just going to be less able to spread out. So you can reduce band broadening by turning up your flow rate. That also has the added benefit that it decreases your retention times and speeds up your chromatography. But it's not necessarily always ideal to crank up your flow rate super high, because cranking up your flow rate also increases broadening due to what's called finite mass transfer, or more simply, the equilibration time of your analyte moving from your mobile phase to your stationary phase. So your analyte, of course, is going to be spending some amount of time in the mobile phase, some amount of time in the stationary phase. And so if the mobile phase is moving too quickly, the stuff that's in the mobile phase is going to get separated from the stuff that's on the stationary phase. And since these guys are always interchanging, if the mobile phase is going really fast, the stationary phase's rate of picking stuff up and letting it go is staying the same. So essentially what you're doing with a high flow rate is smearing your analyte across the stationary phase. So higher flow rate means more smearing due to this finite mass transfer, more smearing of your analyte along the stationary phase, and higher flow rate also means less broadening due to longitudinal diffusion. So all 3 of these mechanisms are combined into an equation called the Van Deemter equation. So the Van Deemter equation just is a way of calculating this value h, which I'll describe or explain in a second. And so we have an a term in the Van Deemter equation associated with multiple paths. So that's just a constant associated with your column. And again, this a term's value can change if you increase or decrease the temperature, but we generally consider it a constant. Next is the term for our longitudinal diffusion. We have a B term describing that, and that is going to be divided by our flow rate down here. And then we have a term for our equilibration time or finite mass transfer, which is C, and that's going to be multiplied by the flow rate. Now, A, B, and C are all properties of the column and temperature, so they can all be improved using different packing techniques, different size beads, etc. But for the most part, we're going to use this equation to optimize separation for the columns we already have. And A, B, and C here are just empirical values, so you get those by measuring them. So what you do is just vary the flow rate and watch how this H term changes. So H in this equation actually refers to what is called plate height. So what we want is a very low plate height. The lower the plate height, the better resolution we're going to get. And I'll explain why we use the phrasing plate height on the next slide. But if I show you how the plate height compares to the flow rate of our mobile phase, you'll notice, so I have three curves here, one for nitrogen gas as the mobile phase, one for helium, and one for hydrogen gas as the mobile phase. But with all of these, if you turn up the flow rate, so you're actually decreasing your plate height, so you're increasing your resolution up to a certain point wherein the plate height starts going back up. So why does it do that? Well, so basically what we're doing is combining three equations here, right? So this A term, its contribution to the shape of these lines is a constant. So it's just some value that's constant down here. So we're basically adding a straight line to a 1 over x line, which is just an exponential decrease like that. And then this finite mass transfer term is just a linear equation. So we're basically combining a constant value with an exponential decrease and a linear equation. So when you're below this inflection point down here, the flow rate is being controlled by longitudinal diffusion, but if you increase the flow rate enough, longitudinal diffusion stops being an issue. But then we get into this regime where the plate height is predominantly controlled by equilibration. All right, so what does plate height actually mean? So again, plate height is a term we use to describe how good of a separation you're going to get with a given column and set of conditions, including column composition, mobile phase composition, temperature, etc. But the H here, this plate height, is a carryover from something called distillation chromatography. So this is something that historically has been used to separate crude oil into its different components. So crude oil obviously has a lot of components. And so what's done in distillation chromatography is you heat the crude oil really hot and you spray it onto a plate here. And these plates, they have little spaces or little valves where if it's in a gaseous state, it can get up through that valve and drop down or move up to a higher state. And so let's say you have some components in here that are still liquid at 350 degrees Celsius, but some that boil off. Well, the ones that boil off are going to come up through this little valve here and get trapped in this new part of your chamber. But we're applying heat at the top of this chamber and we're actively cooling it at the top. So we actually get as a temperature gradient from top to bottom of this chamber. And so the stuff that was boiling at 350 degrees Celsius, if it moves up to a few of these plates and now it's in a range where the temperature is 250 degrees Celsius, well, some of that gas is now going to condense, but some of the materials are still going to be volatile in the gas phase. They'll drift up to another plate where they can condense at that temperature. And then if it never reaches a temperature where it can condense, it can come out the top of this and be collected as gas still. And so what this does is at these different temperatures, you're going to get different sized hydrocarbons condensing and being in the gas phase. So you can separate out a few different species in here. So the more plates you have in this distillation column, the more separation you can get for the different species. So for example, if you add a few more plates in between the ones shown, you might be able to separate C5 through C7 and then C8 through C10 as separate samples. So the analogy of plates increasing your separation is one that's carried over into modern day chromatography. There are no plates in columns, and I'll repeat that, there are no plates in our columns. The language doesn't really make sense without the historical context. Now it's just used as a theoretical value to describe the quality of our columns, okay? Okay, so if we're going to quantify the effectiveness of our columns, we're going to have to figure out how many plates or theoretical plates are in our column. And again, there are no plates in our column. This is a purely theoretical value that we use to describe the quality of our column. But we will determine the number of plates using one of these two equations right here. So the one on the left is the one we'll use more often. So what this is the number of plates is equal to 5.55 times the retention time of a peak squared divided by the width at half height of that peak squared. Now you can also measure the width at the bottom of the peak, so the full width there, in which case this 5.55 turns into 16. And so this calculation is for a single peak. You don't need 2 peaks or 3 peaks. You'll just pick a single peak to do this calculation on. And then we calculate the height of our plates. So this is basically a measure of how far apart our theoretical plates are. Again, this is vocabulary being drawn from that distillation chromatography setup. But all we do here is we take the length of our column. So let's say it's a 10 centimeter column. You'll divide it by the number of plates, and then you'll say it's 0.01 centimeters per plate, something like that. And I'll give you a practice problem in a sec for you to work on that. So L again is just the length of the column, and smaller plate heights means more plates, and that means narrower peaks, which is what we want. Here's a practice problem for you. An analyte elutes with a 407-second retention time and a half-height peak width of 13 seconds. The column length is 12 meters. What is the plate height for this column? So these are the equations you'll need for this calculation. So go ahead and try and work that out, and I'll go over it in a second. So pause the video. Okay, so let's calculate our number of plates first. We take that 5.55, that's a constant, times 407 seconds. That's the retention time on the column. We're going to divide by that half-height peak width of 13 seconds squared. We plug all that into our calculator, and we will get 5,440 plates. Now, plates, in reality, do not have to be whole numbers. They can be decimal places, etc. That's okay because, again, these are just theoretical plates. And theoretically, you can have half a child or half a plate. And then we would calculate the height by taking that 12 meters, that is our column length, divided by the number of plates. And that will get us 2.2 millimeters per plate, or a plate height of 2.2 millimeters. So the next question is, do all species have the same plate height? Theoretically, they should. However, they don't always give exactly the same plate height, just like when you measure the volume dispensed from a pipette. It's not always exactly the same. So there is some variability, and there is some drawback to using this model of plates and plate heights, and that it doesn't perfectly describe chromatography, but it does a good enough job in JC and HPLC that we haven't abandoned it or try and move on to a better mechanism because it's good enough for what we use it for. Okay, now let's talk about just 2 issues with chromatography that come up from time to time. And those problems are fronting and tailing. Here is a little meme with What's Her Bucket from that MTV show. I'm pausing so you can read it now. All right, but fronting, what this is when the front of your peak looks normal, but then the back of your peak just kind of disappears. So fronting is usually a symptom of overloading your column, so you put too much sample on your column. To give you a better idea of what's going on there, let's say these gold bars here are the walls of our column. And these are analyte molecules here, and right now they're spread out into a nice distributed peak. But as they come in here, if you have too much analyte, you're going to saturate the walls of your column, and that's going to make it impossible for new analyte to stick to it or interact with it, so it's just going to keep flying by, and then all this saturated stuff is going to come out all together and basically give a flat back to this analyte cluster of molecules. And that flat back is basically just going to perpetuate as it moves through the column. So in space, what this is going to look like is you're going to have a peak that looks normal on the front coming out, but it's going to cut off abruptly. And then because we are measuring from this side first, and so this side's going to reach the detector first, we're going to sample through in this direction, and our peak in our chromatogram is going to look like this with a missing tail. The second problem is tailing. That's when a car is in hot pursuit behind you. But tailing is the opposite of fronting. The front of your peak still looks fine, but the back looks spread out. So instead of it being chopped off, it just keeps going into a long tail. And tailing is usually a symptom of your analyte sticking a little too much to your column. It's usually either that you've chosen the wrong column and your analyte has too much affinity for it, or it means that your stationary phase might be starting to deteriorate. It might be time to get a new column. And you might have noticed that my background for today is Pharrell Williams. This is a picture of him from his music video for the song Happy. My background is Pharrell Williams today because he has a song called Fronting. I have not watched or heard that song before, but I have heard his song Happy before.